Okay, so good evening, everyone. I am Master Arnav Birari. I am in 10th grade from Silver Oak Universal School, Nashik. And today we are going to learn about radiation mechanism, as you all might have known. So just let me present my screen, and by the time I will switch off my video to avoid any network congestion. So just let me present my screen. I hope my screen is visible.
Yes, it is visible, Arnav.
Yeah.
Okay. So I guess my first slide is visible, right? Hello.
Yes.
Okay.
But still, I guess the entire presentation is not showed up on the screen.
I am presenting it. I'll again present. So is it visible now?
In the full screen mode, it's not yet presented in full screen mode.
Okay. Maybe I should represent.
Yeah.
I guess it's visible now.
Yeah, you can full screen your PPT and I'll tell you whether
Yeah, it's visible now, I guess.
it's visible now. You're pretty good to go.
Okay. So in this lecture, we are going to learn about radiation mechanism. So what is radiation mechanism? Radiation mechanism is actually very simple than you think. So radiation mechanism is the interaction of dust and stellar atmosphere, or the atmosphere of stars and all the heavenly bodies in a universe with radiation. What happens to the particles of these media and the dust is what we cover in radiation mechanism. Okay, so what is the use of radiation mechanism? What are the applications of studying the radiation mechanism? So by studying radiation mechanism, we can find the composition of interstellar dust, or interstellar dust and stellar atmospheres, or the atmospheres of stars, through spectroscopy. So spectroscopy is actually, in short, a branch of physics in which you find the composition, or you identify the chemical element or compound by identifying the, or by taking observations of the light emitted by it. Okay, so spectroscopy deals with only the visible part of the spectrum, while radiation mechanism deals with the entire electromagnetic spectrum, the interaction of particles with all types of radiation. Okay, so it helps us in identifying what stars and the atmospheres of exoplanets or anything in the universe is composed of. Then it is also helpful in finding the age of celestial bodies. Now, we know that a star has different life stages like a human being, and it is composed of different materials during its entire lifetime. As a star ages, the amount of metal content in it increases. Okay, and if we if we get to know what a star is composed of, then we can also technically find its age. If a star is mostly composed of hydrogen, helium, or any lighter elements like beryllium, boron, or anywhere around carbon, then we can say that the star is pretty young. And if it composes elements such as scandium, calcium, or in elements around iron, we can say that it is approaching its death. Okay, so the third application is explaining various solar processes such as solar storms. Now, this is still a field of study because we have observed that the atmosphere of sun is many times hotter than the actual surface of the sun. Okay, so scientists are trying to explain this with the help of radiation mechanism, but it's not a foolproof theory now. Like research is still going on it. And the fourth application is detecting the motion of celestial bodies. Now, we know that our universe is expanding, and even the stars and planets are not like at rest with respect to each other. Okay, so if we want to know whether a star is moving away from us or it's moving in which direction, at what velocity, we just observe the light emitted by it. If the light emitted by it is shifting towards the red spectrum of the visible light of, or red spectrum of the electromagnetic spectrum, or to the blue part of the electromagnetic spectrum, we can tell its velocity, its direction of motion, and the cause of its motion many times, like mostly. Okay, so these are some basic applications of radiation mechanism. Then we move forward to some very basic concepts which are essential for understanding the radiation mechanism. Okay, so we all know that an electron is composed of a nucleus with a swarm of electrons around it. And these electrons happen to be in different energy levels. Now, why do electrons possess energy? I'll just tell you in short that electrons are attracted by the nucleus, but they are still not pulled towards it. They are rather in orbit, so they must have some energy in them. And and the closer an electron is to the nucleus, the lesser the energy it has. Okay, so electrons in the outer reaches of an atom generally tend to have greater energy, but according to quantum mechanics, according to quantum mechanical theories, an electron can't have any arbitrary value of energy, or an electron can have only specific values of energy. It can only be in specific energy levels, okay, which is denoted in this picture, as you can see. And another thing is that an electron tends to change its energy level upon excitation or upon any changes in energy. Okay, so this formula right below the picture tells you the relation between the energy change in the energy of electron and the electromagnetic and the frequency of the electromagnetic radiation it emits. Okay, so here H is the Planck's constant, and nu is the frequency of the radiation emitted by it, and EI and EF are the initial and final states of the electron. Okay, so this is a simple relation. This is the basic relation. This is the fundamental relation of a radiation mechanism. Okay.
Excuse me, sir.
Yeah.
Sir, could you please take to the previous slide?
Yes.
Sir, here the subscript to the frequency IF, what does it represent?
It represents the the electron is transiting from its initial energy level to its final energy level. So it represents the frequency frequency of the light emitted when the electron transits from the initial to final energy level.
Okay, thank you, sir.
Okay. So any more questions, or shall I proceed?
Yes, sir, you can proceed.
Okay. So as we know that an electron emits energy in the form of radiation when it changes its energy level. And generally when an electron moves from a higher to a lower energy level, it emits energy, or basically it gets rid of the excess energy uh, as its energy level is decreasing. So that phenomenon is called emission. Okay, and emission is a phenomenon which occurs in hot gases. When you observe any hot gas and you find it and you look at its spectrum, you will see all the wavelengths of, or you will see characteristic wavelengths emitted by the gas. Now, these wavelengths are characteristic for every element. Like a compound, let's say methane. If you see hot methane gas, it will have a particular emission spectrum. Now I'll just like to show you the emission spectrum. Yeah, so this is an emission spectrum and this is an absorption spectrum. So this emission spectrum will be different for different compounds and elements, as it is a characteristic of each element or compound. And this is the absorption spectrum, or this shows the these black lines are actually the wavelengths of radiation absorbed by that atom, absorbed by the molecular atom of that compound or element. Okay, so yeah, one thing I forgot to tell that as we know that emission occurs in hot gas, in the same way absorption occurs when, or absorption is noticed when we see a cold gas against a source of white light, or against a source which emits all the colors of light. Okay, so through this process we get the absorption spectrum, and by taking the spectrum or taking the light emitted by a hot gas, we get the emission spectrum. While you can see here is the continuous spectrum, or basically the entire spectrum. Okay, and this is the same formula which we studied earlier. Here the delta E is replaced, or the EF minus EI is replaced by delta E. So there are now various types of emissions. One is spontaneous emission. Spontaneous emission occurs almost all the time, or whenever an electron emits radiation, whenever an electron emits radiation, it is emitting it spontaneously. So how does spontaneous emission occur? So as you can see here, an electron is in its ground state. Now, ground state of an atom refers to the lowest possible energy an electron can have around the nucleus, while being around the nucleus. Okay, it is also the closest shell in which an electron can be. Now, there are some certain rules according to which the distribution of electrons in various shells is done. Like so not all the electrons can be in the first shell, only certain number of electrons can be in the first shell. So an electron in its closest possible shell to the nucleus is said to be in its ground state. Okay, and when such an electron absorbs a photon, or when a photon strikes such an electron, that photon transfers its energy to the electron, and the electron may or may not get to an excited state. Now I am saying may not because we have studied that an electron or the energy level in which an electron can be are quantized. So not all not all photons can excite an electron. Only photons corresponding to the difference in the energy level of that electron can excite the photon. Okay, so if this photon has exactly the energy required for exciting the electron, it would excite it, or it would move it into a higher energy level. Now, this electron generally doesn't stay here. Okay, it falls back down. Okay, and this is called spontaneous emission. This occurs most think that the electron should move another energy level up, because a photon is being fired at it, we are supplying it more energy, but it doesn't happen. Rather, it moves to a lower energy level. Instead, even though we are firing energy to it. So this phenomenon is called stimulated or induced radiation. So what the photon is causing here is that this photon is actually supplying the energy, or it is basically irritating that electron and causing it to emit another electron, or not, sorry, it is irritating that electron and causing it to emit another photon of the same frequency. Like, see, we know that an excited state of an electron is quite unstable. So if we, in the excited state, if we fire another photon, that electron won't go to a higher energy level. Rather, it would emit two electrons and get back to its lower state. Sorry, two photons and get back to its lower state. And it is seen that in the spontaneous emission, when an electron emits spontaneously, the radiation emitted by it is isotropic or incoherent. Isotropic means it is spread in all directions. The radiation emitted by an electron during spontaneous emission has the probability of going into all directions. We can't tell from which direction would it come. But in stimulated or induced radiation, the thing is a bit different. The thing is a bit interesting. In stimulated or induced radiation, the electron would emit the two photons in the same direction as the incident photon. Okay, and this special property of, or this special phenomenon has made us make use of stimulated or induced radiation in lasers. Right, lasers can be said to be a concentrated beam of photons. Okay, so if whenever you see a bulb is emitting radiation in all directions. But in a laser, we are implying stimulated radiation and thus concentrating the amount of energy which would have been emitted in all directions in case of spontaneous emission into a single beam towards a single direction, which happens induced or simulated emission. So lasers are the most prominent example in where stimulated or induced emission is implied. So these were the two types of emissions, and now we will study ionization recombination in astrophysical terms. Okay, so and now the zero energy of an electron is like it is set such that an electron in an atom, an electron bound in an atom will have negative energy, while an electron outside an atom will have positive energy. Okay, or in simpler terms, we can also say that if an electron bound in an atom has negative energy, that means it owes some energy, like uh, it has some deficit of energy. That's why the nucleus has attracted it towards itself. And if we want to free that electron from the clutches of nucleus, would uh, we would require that negative amount of energy. We would need to impart that negative amount of energy to bring it of out of the atom. Okay, so if such an electron with negative energy inside the atom, okay, is given that magnitude of energy, it will definitely leave the atom. Okay, and this phenomenon is called ionization, but in astrophysical terms we called it bound free transition. Transition means change, and bound free means the electron was earlier bound inside the atom, but now it's free. We provided it the required energy and now it's free, so we call it bound free transition. Okay, and unlike what we saw earlier, that for an electron to transit from one energy level to another energy level, specific amount of energy was required. But it's not the case in ionization or bound free transition. We can supply any amount of energy to like any amount of energy will be okay for that electron to move out of the ionization. Just one thing, the energy should be above a particular value. Because the electron has to escape the atom, so it would require the energy which is higher than the highest energy level in that atom. So once any value of energy which is higher than the highest energy level in the atom is supplied to the electron, the part of energy which is required for transiting that electron from its current energy level to its outermost to the highest energy level of the atom will be utilized in doing so, but the rest of the energy will be converted into the kinetic energy of electron. Like I will explain you with a pen. So if an electron, so if this is an electron, and if we have supplied, let's draw another energy level here for understanding. So if this is an electron, okay, it requires, let's say, -5 electron volts of energy to get into the highest energy level. Okay, and I'm just taking an arbitrary value. And if we provide, let's say, 10 electron volts of energy to this electron, then the 5 electron volts of energy will be utilized by the electron to go into the final shell, the highest energy level, and the remaining 5 electron volts would be converted into the kinetic energy of the electron. Okay, so in this way, all values of energy will be accepted by the electron, unlike that in the transition between two energy levels. And the same opposite of ionization is recombination. Recombination occurs when an electron is captured by a nucleus. Okay, and in recombination, we saw in ionization an electron needs energy in the form of radiation or in the form of photon to get out of the atom. But in recombination, an electron emits a photon of a certain frequency nu to enter into the nucleus. See, it has to enter the nucleus, so it has to shed the extra energy, because to be in the nucleus, it has to have negative energy, and being outside the nucleus, it has positive energy, so it has to shed that extra energy. So that extra energy is shed by the electron in the form of radiation. Okay, now these are some different types of transition. This is free. I'll explain this to you a bit later. First, let's start from this. So this is what happens in absorption. Every electron or any electron moves from its ground state to any excited state. Excited state is any state above the ground state, any energy level above the lowest energy level. So whenever an electron moves from its ground state to any excited state, or from a lower energy level to higher energy level, it's absorbing radiation. Whenever an electron moves from a higher energy level to a lower energy level, or from an excited state to a ground state, it's emitting energy. It's shedding off its energy. And wherever an electron is moving from nth energy level of an atom directly outside the atom, it is undergoing ionization or bound free transition. Okay, and whenever an electron is entering into one of the energy levels of an atom, it is called free bound transition. I forgot to tell this, but recombination is also called free bound transition. First the electron was free, now it's bound, so free bound transition, as simple as that. And absorption is also called bound transition. Why? Because electron was initially bound and still it is bound, so bound transition. Emission is also the same, bound transition. Okay, these are just simple terms for absorption, emission, ionization, and recombination. And then the fourth type of transition is the free transition. Okay, so now normally what happens, like in some cases an electron scatters from a nucleus or ion without being captured. Or basically, scattering of an electron in simple terms is change in the trajectory or deviation in the path of an electron while it passes a nearby atom. Okay, so when an electron scatters from a nucleus or an ion without being captured, the electromagnetic interaction refers to the electrostatic interaction between the nucleus of the atom and the electron. Okay, due to this interaction, that electron may speed up or it may slow down. Okay, like in the same way as we have seen, as we may have seen a spacecraft while it takes a flyby of any planet, the spacecraft usually speeds up or it slows down depending upon the trajectory set by you. Okay, in the same way, an electron may also speed up or slow down due to the electrostatic influence of the nucleus on it. Okay, now whenever the electron decelerates or whenever the electron slows down while passing a nearby atom, it emits radiation. It emits radiation because energy is something which has to be conserved. If it's like energy, if it's going somewhere, if the electron is decelerating, it must radiate that energy. That's why energy is radiated whenever an electron decelerates, and this radiation is what we call free radiation. The electron was free, and after the interaction it's still free, so we called it free radiation. And this generally occurs in a very hot gas, at temperatures exceeding 10 to the power 6 Kelvin. Okay, these temperatures are generally found in stars, and in stars where there are only hydrogen or mostly hydrogen and helium atoms present. Okay, so under this temperature, even hydrogen, which is said to have one of the highest ionization energy, is ionized. Okay, and under this condition, when hydrogen is fully ionized, then under this condition, the free radiation has been given a special term called thermal bremsstrahlung. Okay, I'll just write it. It is given a special name called thermal bremsstrahlung. Okay, a thermal bremsstrahlung is just a type of free radiation which occurs under very high temperatures exceeding 10 to the power 6 Kelvin. Okay. So this was a phenomenon. Then let's move forward. Now we are going to see about what is polarization. Okay, polarization. Okay, so first let's understand what actually an electromagnetic wave is. So just a minute. So is my paint screen visible?
Yes, sir.
Okay, so yes, as we know of, and light wave is a transverse wave and is composed of two oscillating fields. First is electric field and the other is magnetic field. Okay, so to study polarization, we are just dealing with the electric field and now let's say if I'm an observer, okay, and from this angle I would observe this wave in, let's say, this orientation, where this point is actually this line, this direction of propagation of wave, like this is the line and this would be the vertical or the electric field. Just think about the cross section of this wave that generally doesn't exist, but think about the cross section of this wave, like observing, like cutting it right from here and then observing it. One would see it in this form. Okay, so in a non-polarized wave, you would generally see the electric field oscillating in not one direction but in many directions. Obviously the direction is perpendicular to the direction of propagation of wave, but still there are many directions possible. I will come to it later, but you must know that non-polarized wave is observed almost everywhere. The bulb in your room or the tube light in your room, even the light from sun is non-polarized. Okay, so non-polarized radiation has different directions of the electric field. Okay, like in this case actually I've drawn a polarized wave, but a non-polarized wave has uh, generally different directions of electric field. The electric field maybe in this direction, like it may be oscillating vertically but be still perpendicular to the direction of propagation of wave, or it may at some point it may be oscillating diagonally. Okay, like at this point if I take an observation, I may get vertical oscillation of the electric field. At this point I may get uh, diagonal oscillation of the electric field. At some point I may get horizontal oscillation of electric field, that or basically at every point the direction of electric field oscillation varies. Okay, so this wave is a non-polarized wave, okay, with no fixed direction of oscillation of electric field. But in a polarized wave the electric field oscillates in just one direction, just a single direction. Okay, in the entire wave the electric field oscillates in just a single direction, like I've drawn here. It's oscillating in just a single direction. Okay, so this is a polarized wave. Now there are still different types of polarized waves. Okay, so as you can see here, there are different types of polarized waves. First is linear polarized. In linearly polarized wave, the electric field has a single direction, and the graph traced by the electric vector is just a straight line, as you can see here. But in this and okay, so this is the most simple type of polarization. This is linear polarization. Now, what is circular polarization? Circular polarization occurs due to the interference of two waves which have their electric fields polarized. Both of the waves have their electric fields polarized, but they are such that the electric fields are perpendicular to each other. Okay, and one more thing to be added, they both are 90-degree out of phase. Okay, they are not perfectly in sync, or their troughs and crests don't match perfectly. Okay, they are 90-degree out of sync. Then in such a wave we get to see circular polarization. Okay, or the electric vector overall traces a circle. Okay, then there is elliptical polarization. When a circularly polarized wave, in a circularly polarized wave, when the amplitude of one of the wave varies, or it's slightly less or greater than the amplitude of oscillation of the other wave, we get an ellipse out of the electric vector. Okay, so this is elliptical polarization. Okay, so these are the three types of polarization. Okay, so next is Faraday rotation. Now we learned about polarized waves. No, Faraday rotation is actually it occurs when it's passed through a magnetic field. Okay, when such a wave is passed through a magnetic field, the electric field will tend to rotate. Okay, and that amount of rotation, sorry, that rotation is called Faraday rotation, and that amount of rotation generally depends on these factors: wavelength of the wave. So greater is the wavelength of the wave, greater is the rotation. This is basically the Faraday rotation is directly proportional to the square of the wavelength. Okay, So even a slight increase in the wavelength will mean greater Faraday rotation. Okay, so naturally, uh, blue part of the spectrum will undergo greater Faraday rotation compared to the red part of the spectrum. And then the second factor is the component of magnetic field in the direction of propagation of wave. Okay, magnetic field being a vector quantity can be split into its components, and greater is the component in the direction of propagation of wave, greater will be the angle by which the electric field rotates. Just remember that the electric field is polarized here, so the electric field will be uniform. Okay. Then third is distance traveled to the magnetic field. Greater is the distance the wave travels to the magnetic field, greater will be the rotation. It logically, it seems correct, because greater the time for which force is applied, greater will be the displacement. So in the same way, the magnetic field applies force on the electric field. So greater is the distance through traveled by the electric field, greater will be the rotation, because for greater time it will be passing through that magnetic field. So the fourth factor is number of electrons in the path of the wave. It is now Faraday rotation is also directly proportional to this. More the electrons, more will be the rotation. Okay, so these are the four factors on which Faraday rotation depends. Then another interesting phenomenon which we might have known but we generally tend to ignore is scattering. Okay, scattering is a type of spontaneous emission. We generally describe or generally see the most prominent type of scattering is Rayleigh scattering, which occurs in an atmosphere. So what is scattering? Scattering occurs when an atom absorbs an electron. Okay, absorbs an electron, but not electron, sorry, sorry, my bad, not electron, but a photon. When an atom absorbs a photon, then the electron around it excites. Naturally, it would excite, but the atom spontaneously emits that photon with the electron going back to its lower energy level. Okay, so this is a type of spontaneous emission, and in this case, generally, the photon which is emitted can be emitted from any direction. If the photon is incident from this direction, it may be emitted in any arbitrary direction. And another interesting thing is that uh, this phenomenon occurs in our atmosphere. It is called Rayleigh scattering. It is higher the wavelength, higher will be the Rayleigh scattering. That means it is greater for the blue light, the blue and violet light. That's why the light from the sun incident on Earth, the blue part of that light is scattered everywhere in the atmosphere. So we generally see the sky blue. Okay, while the remaining light from the sun is generally seen yellow or green, because the blue part is scattered. That's why what remains is yellow and green light. Okay, so that's why we see sunlight is yellow and green compared to the light emitted by any LED in our house. Okay, then yeah, and one more thing is that the scattered radiation, the radiation emitted by an atom after the electron goes back to its ground state, is polarized. Okay, it is polarized. Then now let's up till this point, we did all the qualitative analysis of what happens to an electron when it accepts a photon, or when it a photon strikes it, and what happens when it emits a photon. But now we are going to actually find what energy would be required to excite an electron, or bring it to its ground state. Okay, so let's start from the Bohr's first postulate. Okay, so the Bohr's first postulate is quite simple. It states that the angular momentum of an electron must be a multiple of h bar. H bar is actually Planck's constant upon 2 pi. We did not to go into its derivation, but we just need to know this postulate. So it is basically this, where mvr is the angular momentum of that electron, and n is any integral value, any positive integral value, and h bar is our h upon 2 pi. Okay, so n is actually any principal quantum number, rather than saying integral value. N can be n is the number of nth, or we can say It is the nth shell of an electron, not an electron, sorry, of an atom. Okay, so this is the Bohr's first postulate. You must remember this equation because we will need it later on. Okay, then is Bohr's second postulate, which states that an electron moving in an allowed orbit around a nucleus does not radiate. Radiation is emitted only when an electron jumps from a higher to a lower energy level. Okay, according to Maxwell's theory, that any charged particle which is in accelerated motion must emit energy. Okay, and thus same should happen with an electron. According to Maxwell's theory, that an electron being in accelerated motion around the nucleus should emit energy, and gradually it should spiral down toward the nucleus, uh, getting disintegrated. But this does not happen because the laws of quantum mechanics are completely different. That's what Bohr stated, that an electron does not go towards the nuclei, it does not spiral down towards the nuclei, because classical mechanics law aren't applicable on it. That sounds funny, but it is what actually Bohr stated. And he also stated that an electron can have only specific energy levels, like I said earlier, and this is the same formula which we earlier saw. Okay, so this is the Bohr's second postulate. Then now let's try to find the force exerted by the nucleus, or rather than saying the nucleus, a single photon on a single proton on an electron. Okay, we need to find out the energy emitted by the electron during its energy level transition. So first we will start with the force which is exerted by a proton and an electron. Okay, so we know Coulomb's law, which gives the relation for the force acting between two charged particles. Okay, so this is the relation, and we can slightly modify it to fit for electron and proton. Now this is the same K which we are talking about, the Coulomb constant, and q1 and q2 are the charges of an electron and a proton, but we are considering it as e square here because the charge on a proton and an electron has the same magnitude, though it has this different sign, but it has the same magnitude, so we can consider it as e square, or the square of the charge on an electron. Okay, and Rn square is actually the distance of that electron from the nucleus, okay, or from the proton. Okay, so this is our equation for our electron. Okay, and so then by applying Newton's second law, okay, so we are deriving each single equation which will require for finding the energy of that electron. So this is the third equation which we will need, and that is the acceleration and relationship between the acceleration of a particle moving in a circular motion with the radius Rn. Okay, so this is the relation where Vn corresponds to the velocity of the particle and Rn corresponds to the distance of the particle uh, from the center of the circle which it is tracing out. Okay, then by applying Newton's second law, which is of course F is equals to ma, we get this equation m. Okay, so mv square n upon Rn is actually m into a, m into Vn square upon Rn. So this is what is brought down here, and this is actually the equation of force which we derived on the previous slide. Okay, so we equate both of these, and then on the second slide, on further simplifying the equation, we find the values of the velocity of an electron in an orbit and the distance of that electron from the nucleus uh, while being in that orbit. So these two actually are very interesting relations. So if you want to find out the velocity of an electron in any particular atom, let's say in the atom of gold, the velocity of an electron uh, at the nth energy level in the atom of gold, in any particular atom, you can find this out just for fun, or like it's quite useful equation and it's quite fun solving this. Okay, then the total energy of an electron in the orbit n is now this energy En is the kinetic energy plus potential energy of that electron. This you will learn in mechanics in 11th and 12th. In 11th and 12th, I will not cover it here, or
Excuse
it
me,
would be
sir.
off topic. Yeah.
Sir, here the number of protons, or the what we say atomic number, is not included. So that means the energy for all the atoms in nth orbit would be same.
Uh, kind of, yeah, we can say.
So, but it as we have studied that Bohr's postulates are applicable for hydrogen-like atoms. That means only one electron, but the number of proton varies from atom to atom. So we should have considered the number of protons.
Actually, I don't know in very depth about this, but I can tell you that the number of protons and electrons in an atom are same. So we can reduce the equation down to one proton and electron. If you have the doubt, Prasad sir can clear it at the end of the session. Okay, so just wait till my session gets finished, till my slides
Okay.
get over. Okay. So this is the total energy of the electron, which is its kinetic energy plus its potential energy, and we can simplify it to this. Okay, so this is further considered as C. C is a constant. We can consider because we have considered directly a single constant for it, because everything in here is like constant. Mass of electron, charge on an electron, pi, like then there is vacuum permittivity and h bar is everything is constant. Okay, and then there is just n square, which is the nth energy level. Okay, so this gives us the energy of an electron in nth energy level. Okay, so in this way we can find out the energy gained or lost by an electron when it undergoes any energy level transition with this equation. Okay, and in terms of wavelength, we can express it in this format, like what will be the wavelength of the radiation emitted when an electron undergoes an energy level transition. Okay, now this is further simplified into this, where R is the combined form of C, H, and C. It is also called Rydberg constant. Rydberg constant. Okay, and this is the most simplified form of our energy equation for an electron. Okay, so uh, there were scientists. There were scientists who derived this formula, and they calculated it for different energy levels. Like they calculated energy gained or lost when an electron transits from nth energy level to a specific energy level. Like Lyman discovered, or Lyman found the values for the transition of an electron from nth energy level to the first energy level. In the same way, different scientists such as Balmer, Paschen, Brackett, and Fund found it for nth energy level, found the energy values for transition from nth level to any two, third, or fourth. Like okay, so according since they found it, these specific transitions are named after them. Okay, and one thing to say, these are all for the hydrogen atom. Okay, these transitions are for the hydrogen atom, so it would differ for different elements. Okay, so the transition from nth to first level is Lyman, from the nth to second is Balmer series, from the nth to nth energy level to the third energy level is Paschen series, and from nth to the fourth energy level is Brackett, and so on for Fund series. Okay, Fund is nth to fifth energy level. Okay, and this is I guess this is the emission spectrum of hydrogen, if I'm not wrong, because I'm not able to. Yeah, it's emission. Yeah, I guess it's emission spectrum. Okay, and that's all for the lecture. Thank you. If you have any doubts, you may ask them by unmuting yourself. Okay, so if you have any doubts, you can ask. Okay, Kushi, you want the definition of Faraday rotation?
Yeah.
Yeah, Faraday rotation is just simple. We know you understood what is polarized light.
Yeah.
Okay, so whenever a polarized light with its with its electric field in a particular line or in a particular orientation, whenever such a light wave passes through a magnetic field, then it undergoes rotation, or basically the electric field rotates. Okay, the electric field rotates. So
Yeah.
that is what called for, that is Faraday rotation. Okay, Aditya, Bohr's first postulate. Okay, Bohr's first postulate. Just let me go to the slide. Bohr's first postulate is simple. It just states that whenever we know that electrons are in an atom around the nucleus in nth shell. An atom has different energy levels, and if an electron is in nth shell, the angular momentum caused by it will be an integral multiple of h bar. H bar is h upon 2 pi, where h is the Planck's constant. Its value I can tell. Just a minute. Its value is like 6.625 into 10 to the power minus 34 joules second. You also get it on Google, so no need to worry. So the angular momentum is the integral multiple of that value. Okay, and that integral multiple is actually the principal quantum number or the nth energy level. Okay, like n is similar to KLMN designation. K is 1, L is 2. So it's as simple as that. So any other doubt on Faraday rotation? Yeah, it is directly proportional to the wavelength square. It is. And sir, I guess Khushi or someone had a doubt which I cannot answer. Prasad sir, are you there?
There was okay. There was one question
Yeah,
in
you may
middle.
address the doubt.
So who had that doubt can unmute themselves and ask it.
Sir, it was me. I was asking that Bohr's atomic model is applicable only for single electron species, like hydrogen-like species. But the number of proton varies from atom to atom. Like for hydrogen, it is one. For lithium, it would be three. So we should have considered the number of protons in the equation because it is important, or otherwise the energy in any atom at any nth orbit would be same for all, and that's not possible.
Yeah, the thing which you're saying is just see, Bohr had that analysis just for the hydrogen species, and if you want to extend it, you can see basically it's product of the charges, right? So once you know, only one scaling factor will be added. Okay, like for example, if you want to take product of two charges, and we all know that the charge on electron is same as that of the charge on proton, right? So what
Yes,
basically will come out of that, force expression will be n times E will be the total charge on the electrons, and n times P will be the total charge on the protons, right? So that P
yes,
can be equated to E. So E square will integrally remain constant, but additionally, what you can take out is n from Ne and one n from NP, right? So n square will be just a scaling factor which gets itself into the equation, and that's how you can generalize that thing for the higher orbits.
okay, sir.
Yeah.
Thank
There
you,
would be
sir.
just a scaling factor that will depend upon the number of protons or number of electrons, which is nothing but the atomic number. So atomic number scaling is included if you want to generalize a discussion for the higher species, except for the hydrogen.
Yes, sir.
But it is not always as easy as just putting n, okay? Because once you'll see in BSc physics, or like, and as into the context of the MSc physics, the things are quite more different than the ones which I've told right now. But just for the sake of simplicity and to have a very approximate analysis, you can do what I told you now. But things basically vary on the ionization potentials also, and some higher order transition level physics also. But what we can generalize as of now is to just take it as n times E and n times P, and you can take a scaling factor outside the equation. It just gets scaled by a multiple number.
Yes, sir.
Any more doubts? So
And
should
sir,
we
is the
start with
couch
that?
session ready, or we should
Yeah,
take
it's
it in the
ready.
next session?
So should I be sharing my screen now because
Yeah,
I'm
it
on
would be
mobile
nice. It
phone?
would be great.
Okay, fine. I'll share my screen. Sorry for the inconvenience because I'm on my this thing today, mobile today.
Okay, so we are just having a quiz session now, and you can play that quiz by, we will just share a code. You can just put it on
Okay,
Kahoot
so I'll
app.
briefly give you how to join the quiz. You can put Kahoot.it on Chrome. Okay, so there will be a page wherein it will redirect you to play a Kahoot quiz, and it will ask you for a pin. Okay, so I'll be sharing pin with you. You can see on my screen. So just put Kahoot.it on Chrome and put the game pin, which you will see on the screen right now. And once you'll put the game pin, you have to see question on my screen, and you have to mark answer on your screen. Okay, the answer will be in form of colors, color options on your screen. So for example, if you see the option in green to be the correct answer, then you can mark the green symbol on your screen and have your answer noted. Okay. So we'll play a very small quiz. So is my screen visible? Is
Yes,
my
sir, it's
screen
visible.
visible?
Yes, sir, it's visible.
Okay, fine. It's creating a game pin because on laptop it's quite easy. Okay, it's taking a few extra seconds to load. It's still loading the game pin. See, this is the game pin 9638556. Is it visible to everyone on my screen?
Yeah, it's
Yes.
visible.
Okay. So I'm waiting for the players. You can just join at www.kahoot.it. It will ask you for a game pin. You can provide this pin and log into the game. Okay. So I'm still waiting for the players to join. Okay, Anuj has already joined. There is anonymous. It will be better if you can join with your name so that we can have you featured, or we at least get to know who is scoring more. She has joined. Are there any more students who are joining? Noj, Anonymous, and Khushi have already joined. So I'm waiting for the other students to join. I'll wait for a minute now and then we'll start. It's easy. You can just join from www.kahoot.it. You can put it on your Chrome. It will ask you for a game pin. You can provide the pin which you are right now seeing on the screen. And once you provide the game pin, put a valid name, candidate name, and then you can start log into the game. So are there any more candidates who are joining? Arnav?
I can just wait for a minute or two for anyone who's joining.
Okay. Because Khushi, Anuj, and someone anonymously have joined.
It's there on the screen, Rajpal.
Okay, so I'll start with the game now. So opening mystery box of radiation. So the first
Sir, I
question
lost the
is,
pin.
hot gases have pin is 9638556. So hot gases have first emission spectrum for red, absorption spectrum for blue, discontinuous spectrum for yellow, and none of the above for green. You can see the game pin down right on the right hand side of the screen. Okay. So all of the three have got the correct answer, that is the emission spectrum. Let's see who is leading the scoreboard. So it's Anuj who is leading the scoreboard, followed by Khushi and then Rohan. So question 2 is, an electron stays in excited orbit for around few seconds for red, few microseconds for blue, few nanoseconds for yellow, and few picoseconds for green. An electron stays in excited orbit for around few seconds for red, few microseconds for blue, few nanoseconds for yellow, and few picoseconds for green. Okay, so the correct answer is few nanoseconds, and two of you have managed to get it correct. Let's see who's leading the scoreboard. And it's Rohan who is leading now, followed by Anuj and then Khushi. So next question for today is, where is the use of spontaneous radiation excessively seen? Okay. So spectroscopy for red, astrobiological studies for blue, lasers of masers for yellow, and none of the option uses it for green. Where is the use of spontaneous radiation excessively done? It shouldn't be used where it is excessively Done. So all of you have got it wrong. It's basically the spontaneous radiation phenomena is using exciting the laser or the maser in its metastable or unstable state. Okay. So let's see who's leading the scoreboard now. There is actually no one because no one has got the correct answer. So the next question is an electron which transit down during spontaneous radiation basically is stable for red, unstable for blue, metastable for yellow. Any of the above can sustain it. Is for green. The electron which transit down during spontaneous radiation is of what nature? Stable for red, unstable for blue, metastable for yellow, and any of the above can sustain it for green. Okay, so it's basically unstable is the correct answer. Three of you have got it correct. Let's see who's leading the scoreboard now. So actually, it's again Rohan who's leading the scoreboard, followed by Anuj and then Khushi. The next question is recombination will be followed by emission of photon by electron for red, absorption of photon by electron for blue, absorption of photon by atom by for yellow, and emission of photon by atom for green. Recombination process inside an atom will be followed by emission of photon by electron by red, emission of photon by electron for blue, absorption of photon by atom for yellow, and emission of photon by atom for green. So the correct answer is emission of photon by electron. It's how it enters within that particular atom. So this is the correct answer. Let's see. Only one have you have managed to got it correct. So let's see who's leading the scoreboard now. Okay, so it's again Rohan followed by Anuj, and then we have got Viraj into the list now. Next question is which of the following atomic phenomena can be related with gravitational slingshot effect? Okay, so recombination for red, free radiation for blue, ionization for yellow, and emission for green. Which of the following atomic phenomena can be related with gravitation slingshot effect? Recombination for red, free radiation for blue, ionization for yellow, and emission for green. Okay, so the correct answer is free radiation can be related with the gravitational slingshot effect. Let's see who's leading the scoreboard now. It's Anuj followed by Rohan, and again Khushi has gained her momentum and had a very strong comeback into the list. So let's get to the next question. In Faraday rotation, that rotates due to dash. Electric field due to magnetic field for red, magnetic field due to electric field for blue, magnetic field components by magnetic field for yellow, and electric field components by electric field for green. In Faraday rotation, dash rotates due to dash, and options are there in front of you. Okay, so the correct answer is electric field by magnetic field, and four of you have got it correct. So let's see who is leading the scoreboard now. It's Anuj, followed by Rohan, and then Khushi. Blue light of atmosphere can be explained by dash phenomena. It's pretty easy. Emission for red, Rayleigh scattering for blue, polarization of light for yellow, and dissipation of radiation for green. Blue light of atmosphere can be explained by which phenomena from the options given below? The correct answer is Rayleigh scattering, which imparts the blue color to the atmosphere that you see. So now it's Khushi has taken a very big jump and has secured first position, followed by Anuj and then Rohan. Let's see now the game-changing round has started. Which quantum number can be used to signify the energy level? Is it L for red? Is it M quantum number for blue? Is it N for green? Or is it S for M for blue, N for yellow, and S for green? Sorry. Which quantum number can be used to signify the energy level inside a particular atom? L, M, N, or S? By which letter it is basically denoted? Okay, so the correct answer is N. Three of you have got it correct. So it's basically Khushi followed by Anuj and then Anonymous. So last and game-changing question for today is there on your screen. Write down electrostatic forces inside an atom follows inverse dependence on distance for red, direct dependence on distance for blue, inverse cube dependence on distance for yellow, and inverse square dependence on distance for green. It's a very rapid fire question. Answer it fast and gain your position on the leaderboard. Last 2 seconds. And here we come to an end of this gaming round. The correct answer is inverse square dependence on the distance. So let's see the podium. Third position, we have Anonymous. Followed by on second position, we have Kushi Shetty. So the game has changed. And on the first position, we have Anuj. And runners-ups, we have Rohan and Viraj. So thank you so much for playing this game. It was 36% was the accuracy, and we had six difficult
I
questions.
guess you should take the screenshot of the leaderboard.
I took it.
Okay.
So that was all for today, and I hope you enjoyed our session. It basically helped you gain knowledge today, and hope you enjoyed our game, a small gaming session at the end. So thank you all for
And
attending our session today. If you have any doubts, you can ask us, or if you want to share any feedback, you can feel free to unmute yourself
yeah, please
and let
do
us know
share your feedback.
your
Like if
feedback.
you like the session or you
If,
dislike the session, so we can improve.
so we can improve. Anything you want to speak so that we can implement it from the next session itself.
Sir, I have a suggestion. You should extend the time of the session.
Actually, that is something that we have worked upon. We used to have sessions more than 1.5 hours, and we have scaled it down to 1 hour because it was a kind of suggestion that people are not able to grasp a lot many things in in a very single session. So I've reduced the time to 1 hour. It was a very previous suggestion from much of these sessions that we have taken till now. So if you want longer sessions, we can have it planned once in a while. But most of the people do demand for a very smaller session because they cannot grab that amount of knowledge in a single session. So maybe your requirement is depending upon your keenness and openness to this thing understanding. But for you, we can consider and keep some long sessions of 1.5 hours in future, so that students like you can benefit.
Yeah,
And
we'll keep long sessions once we have got the audience one. Like if you are interested, you attend regularly, we can keep for the specific audience because generally
even
people
we
don't
have
attend so
special
long
sessions for students
sessions.
also. We have special session for
Yeah,
students also, like tutorial sessions are there, which are basically extended sessions only. 1 hour we teach, and for a rest of the half hour we take question solving rounds. So maybe we
yeah,
can plan
even
a long
we
question
take
solving
hands on.
session in future. Even
We
we
take
take
hands
hands-on
on
sessions.
softwares such as Stellarium, and we are planning to take on many different softwares in the near future.
Stellarium, we have IRAF, we have DS9 softwares, we have a number of software depending upon what kind of hands-on we have planned. Depending upon, like we had one for photometry also this year. We also had one for rocket science missions also. So depending upon the need of the audience, we have various softwares which we can use to have the hands-on, and those sessions normally are extended ones. So you'll get extended sessions also, but nominally we try to keep it as short as possible because people are not that much generous to attend it to the end. Because starting of the lecture we had more than 30 students, and now you can see only 6 to 7. I guess only 10 are left, if I'm not wrong. 10 students are there now, so that basically happens. And this is a YouTube channel. You can refer our YouTube channel for longer videos. We have basically uploaded them. Even today's lecture will be uploaded after a while.